Probability Introduction with Priyanshi. Hi Priyanshi, how are you doing?
Hi, I'm doing well, thank you. How are you?
Very good, very good. So Priyanshi, today what will you like to study?
I would like to learn some probability.
Are you doing that at school?
Currently, yes, we're taking a look at mutually exclusive events, independent events, non-independent events, and also we're taking a look at some representations we can do of probability.
hmm What kind of representations?
A representation such as Venn diagrams or tree diagrams. So,
So that means you've done quite a bit and you know
yeah.
quite a bit. That's great, that's great. Perfect, perfect. So since this is our first class on probability, let me begin from very basics, okay? So since you know a lot, we'll see all the answers from you this time. So tell me, what is probability?
Probability is when you have an event going on and there's multiple outputs of that certain event. So, but those outputs can only occur if some other type of thing occurs. So there's a chance of them not happening, but there's also a chance of them happening.
Correct.
That's probability. Yeah.
Great. So that's a very good definition. So you introduce a word to us, events. So what is event?
I would say events is something that's taking place or something that probability is acting upon. So event is basically the main thing out of which we have many other outputs, if that makes sense.
So the event could have many outcomes. The outputs, which
Yeah.
you say normally
Yeah.
term used most of the time, is outcomes. So let's say if I toss a coin six times and I get four heads, can I say that the probability of getting heads is 4 out of 6?
Yeah.
So not really.
Oh wait, it's a coin.
Yeah,
So
yeah, it's a coin.
there's only two possibilities,
Yes.
heads or tails. So the probability of getting heads or tails would still be 1/2. So a half.
So, but what really happened was that I tossed it only 10 number of times. Let's say less number of times, right? So out of that, I get one more than the other. So it means that the coin could have been biased. You get the whole idea. That is one idea.
Yeah.
Now, important thing for us to understand here is that when we are talking about events and probability, then there could be theoretical probability and experimental probability. Correct. So we perform an experiment with the coins, and we do see sometimes that while performing this experiment with the coins, we don't really get 50% chances for heads or tails, right?
Yeah.
We may get something more. And the reason could be that the coin is not fair coin. It is a biased coin, which gives you more, for example, heads. Then it may turn out that the probability of getting heads is higher. That is possible. But the other probability which you were talking about is theoretical probability. Now, in theoretical probability, what we see is what are the total number of outcomes and what are the outcomes. So, in this case of tossing a coin, there are only two outcomes, which is heads or tails. Now, we're trying to define our event, and the event is getting a head. In that case, getting ahead is one out of these two events, and therefore the probability is number of successful outcomes. Successful here means which are defined successful with reference to our experiment or the event. The event is to get the heads when we are tossing the coin. So we are looking only at heads. We have only one head out of two possibilities. So favorable chances of the event, which you may say NA, divided by NS in the sample space. We got two possibilities, heads or tails. And therefore, the probability of getting heads in this particular case is 1 out of 2. You get the whole idea.
Yeah. That makes
So,
sense.
in short, what I have summarized here, I would like to summarize here is that when we talk about probability, it could be experimental or it could be theoretical, right? So that's one part. And these two probabilities can be different, right? Especially experimental probabilities are different because the chances are that in the case of tossing a coin, the coin may not be a fair coin, right? And there could be some biases involved, right?
So we could say theoretical probability is more accurate than experimental.
So theoretical probability gives you a better estimate of any experiment, right?
Okay, so it is kind of more accurate.
Now, coming back to practical experimental probability, you have to perform the experiment many, many number of times to come to a conclusion, right? So just tossing it for 10 times may not be sufficient. Maybe you have to toss it 1,000 times and then record and then come to a conclusion. You might get the same answer as a theoretical probability. You get the whole idea.
Yeah, yeah.
So whenever you're doing experimental probability, make sure that it has been done many, many number of times so that you can come to a conclusion. Is that clear?
Yeah.
Correct. We also learned that the probability is basically a ratio of favorable number of times to total number of times. And this ratio is what we are trying to calculate. Either we are doing experimental or theoretical probability. Is that clear to you?
Yeah, that makes sense.
Correct. So the outcomes are defined by the event, right? So what we are trying to do. Also, when we are trying to do, so I'm mixing up two things here, which is experimental and theoretical, just to give you a base that when an experiment is performed, in that case, there are rules to perform an experiment. It should be repeatable, same type, correct, so that we have exactly the same environment in which the experiment is being conducted, right?
Okay.
And the observations are recorded, and they are not affected by any other parameter. So that
I
is
have
kind of
I have a question.
us, please.
You know the rules that you just said about experiments?
Yeah.
When we look at the weather forecast,
Yes.
that's obviously I think it's a probability because
Yes.
sometimes the weather can be different.
Correct.
But the weather shifts every single day, so
Correct.
there's no possible way that it's in the same environment. Would
Correct.
that still be classed as finding as an experiment, if that makes sense?
Correct. So when we do weather forecast and we are looking into probabilities for weather, then over a period of time, we see in a particular year, there are 365 days, for example.
Hmm.
Over past 25 years, 30 years, what happened? You get the whole idea. So we are taking year as a whole
Okay.
and checking each month if you want to break it down to months, right? Or each day if you want to break it down to day. So that particular day, that particular month is compared over a period of time, which could be more than 20 years. So you get a fairly good idea of how it has been. And of course, things change, and therefore we also see the shift. And we can from there see how the environment is also changing over a period of time since the probability is changing. For example, in Canada, we used to have maximum snowfall in December. But now, lately, we have seen there's a lot of snow in January and February. So the seasons have changed. Correct. And the probability has increased of snowfall in the months of January and February. And it has decreased in the month of December. And normally, there used to be white Christmas, and now we have green Christmas. The whole idea. So, it changes. And you had a very relevant question. So, but what we have fixed is the days, right? And the years, right? And we
Yeah,
are comparing with each day and each year over a period of time. And all these data, they are available for many, many years. I just said 20, but it could be many, many years, depending on which country you are in, correct?
perfect. Yeah,
Correct. So now once we have understood the basics, let's take up some examples and also see how do we draw Venn diagrams and tree diagrams to get a conclusion about probabilities. You right?
perfect. Yeah, yeah,
Simplest of them is throwing a dice. And let me now share with you a whiteboard and then we'll take a few examples. So now let's talk about a fair. So I said a fair dice, right? So we are using a dice. So dice has six sides, correct?
Okay, yeah.
So what could be the outcomes?
You could get any number between 1 to 6.
You're right. So let's write down, list all the outcomes, right?
Yeah.
So we are we have a dice. We are calculating theoretical probability in this case. And if you throw this dice, there are six numbers which could come. Now we have to define an event, right? Now event is normally labeled as some capital letter. Let's say A here. So what is your event? Event, let's say, is when you throw the dice, you want a number which is, let's say, a prime number. So now, out of these six, we have to see how many are prime numbers and what are the favorable numbers for us. Tell me.
I know the prime numbers out of this list are 2, 3, and 5.
So that means 2, 3, and 5, right?
Yeah.
So we are interested in number of prime numbers, which will really give us this result, right? Because probability is a ratio, right? So
Yeah.
the 9 for A. So these are successful number of outputs, outcomes, which are three for us, right? So total number of outcomes are called sample space. So I use S for sample space, and
Oh, yeah.
total numbers is six. And therefore, probability for the event A is the ratio of number of favorable to number of sample space, right? Total, correct? So it is
Yeah.
3 out of 6, which is half. Makes sense.
That makes sense. Yeah.
So we have done our first example with the dice, correct?
Hmm.
Now, let's move out of this and then do another example with the, okay. So let's now work with coins. Now, dice and coins, these are two very popular when we talk about probabilities, right?
Yeah.
So here, the two outcomes which you are looking into are normally heads and tail, right?
Yeah.
So that means if I toss the coin once, I could get head or I could get tail. So what I'm trying to do here is make a tree diagram. So in tree diagram, we show you sequence of events, one after the other. So that's the beauty of tree diagram. Very complicated experiments or cases or events can be depicted on tree diagram and easily we can find probability. We'll see how. Is it okay?
Yeah. Perfect.
So now, let's say this is our first throw. The probability of getting head is half, right? Because there are two
Yeah.
possibilities, and for tail also is half. Now, if I repeat this experiment, right? So, if I repeat this experiment, then what happens? Again, I could get head or a tail, correct?
Yeah.
Either way, right? And the probability remains same, right? Which is half and half for each, correct?
Yeah. Don't the probabilities need to add up to 1?
Yeah. So the chances, if I do with this, let's say earlier in the first throw, I got head. Now again, if I toss the coin, then it could get head or a tail. And if the coin is a fair coin, then 50-50, right? So half and
Yeah.
half, right? Now the idea here is to check at the end, after the two tosses we have done, right? What is the outcome? So if we go with the first branch, which is head and head, right? You see, we get two heads in a sequence, correct?
Yeah.
If I go with the second, if I go first, we have head and then we go to tails. So we have head and tail, correct? As an outcome. If we had a tail first and now head, then we have tail and head, and we could also get tail and tail, correct?
Yeah.
So after tossing the coin two times in a row, what we get two heads, we get head or a tail, or we get tail head, or we get two tails. Is that clear to you? Right. Now, We could define an event. We could have an event. Let's define our event. Is this time, let's say the event will be C. And the event C is defined as at least one head.
Okay.
Now, at least means that there could be one head or there could be two heads. When you
Yeah.
toss two coins, at least one head, when two coins, right? You can
Isn't
say one coin after another. So that is how we are doing it, right?
mhm.
Now, at least two heads, how many are there? So number of favorable cases for C is what? And total number of cases is what? Can you tell me, please?
uh the total number of cases is four,
Yeah.
and out of those four cases, three is the
Yeah.
favorable event.
You are absolutely right. So the probability, we'll write P for probability for getting at least one head is 3 out of 4 when we toss two coins. You get the whole idea.
Yeah.
And with tree diagram, we can visually see it. That's the beauty of it.
Ah, so would that mean, since this is just like an extra thing, because the probabilities need to add up to one, at
Yes.
least if at least one of the if at least one of them is tails, that's one quarter, like one over
Yeah,
four.
one quarter. Yeah. So you could also do with the probability tree. So if you go through the first branch of getting two heads, multiply half with half, right? And you get one fourth as the probability of getting two heads. You get the whole idea?
Yeah,
Then you could go with the second branch and then half and half will give one fourth as the probability of getting head and then tail, right?
yeah.
Similarly, tail and head will give you one fourth, and this two tails is also one fourth. Now, these three are successful events for the case defined, which is at least one head in two tosses or
Ah,
two
yeah,
cases.
that makes
So you
sense.
could add them all 1 4, 1 4, 1 4, 3 1 4 means 3 by 4. Makes sense.
That makes sense. Yep.
Right? So probability tree actually gave you the answer very much, very easily, straight away, also, right?
Yeah, that's true.
That is why we were writing on each branch the probability of the particular event. You get the whole idea.
Yeah, yeah.
Now, at this place, I will also try to define another thing, which is what is the complement of the event, right? So let's try to understand this example further. When I say at least one head, it means I could define another probability, right? No heads.
Yeah.
So if I divine no heads, right,
Hmm.
me, means this becomes complement of C. Correct? In C, we are saying at least one head. And we say, okay, what we could do is total probability, as Priyanshi was saying just now, should be one. We could work with this. That is, no heads at all, right? And there is only one case out of four, right, which gave us no heads, correct?
Yeah.
And therefore, the probability of C now becomes 1 minus probability of not C, right?
Hmm.
Which is again 3 by. So you could also approach this problem by using the concept of complement. Now, this concept is very important. In the present diagram, there were only four cases, so you could easily see them and figure it out, right?
Yeah.
But if the experiment is slightly more complicated, and there are many, many cases. For example, what is the probability of, let's say, in a class, there are 20 students. Now, the question is, what is the probability of having birthday of two students on the same day? Now, that
Well,
becomes a very complicated question.
yeah.
and can be very easily solved by using this function, complementary. So let this be a question for our viewers, right? We'll solve
Mhm.
it in our next class. Okay?
Yeah.
Great. So let's move on. So Priyanshi, can you summarize till now what have we learned about a probability?
I've learned that probability can be divided into two things: theoretical probability and experimental probability. Theoretical probability can be a bit more accurate than experimental probability, and experimental probability can sometimes be unfair because the you use the example of the dice.
Unfair, yeah, yeah, because if
Yeah,
it could not, you're experimenting with the dice, which is not fair.
yeah, yeah.
You come to know only after doing the experiment, correct?
Then we learn rules to experiments because before we can find the probability of something, we need an event to occur or we need to do an experiment. So the rules to experiments are it needs to happen in a fixed place, fixed time, and it should be like repeatable
Yes,
because it needs to be done multiple times to make sure
correct.
that we get accurate outcomes. Then we went to do an example of a dice where we first listed out the outcomes, named an event, and finded the whole probability of that happening. We did the same with a coin, where we used a tree diagram
Yes,
and listed out all the results we could get. I also learned that there's not only one way to approach that question, there's multiple ways. So, yeah.
correct. Great. So let's continue with now two other concepts. One is dependent and independent, and then we'll talk about conditional probability. Interesting?
Yeah.
Great. So let me again share with you a whiteboard. So in this experiment of toss, let's say two coins. In this experiment, you observe that probability of getting heads equals to half. Probability of getting tails is also half, right?
Yeah.
Now, whether you toss it one time, two times, three times, any number of times, it remains exactly same, correct?
Mm-hmm.
So therefore, the events are independent.
Yeah.
Get the whole idea. This is one way of saying it. Second way, let's talk about probability of head, and then again probability of head. Let's say we are tossing two times, right? So the event here, A, is now defined as toss twice,
Yeah.
one after another. And what we are looking at, probability of two heads, correct? So
Mm-hmm.
probability of two heads now is head after head. So probability of first head is half and times probability of the second head, which is 1 out of 4. You see that? So what
Yeah.
has happened? To find the probability of two heads, we actually multiplied the probability of first head with the probability of the second head, and we got the same answer. You got the idea? So how
Yeah.
did we get it? So the probability of first head times the probability of the second head gives us half times half. So if that is true, means the probability of first event times the probability of the second event gives you exactly the same answer, which is the answer. Then the events are independent. You get the whole idea?
Yeah.
Now let's take a case where the events are not independent. Could you give me some example?
Um, if we had, if we replaced something, for example,
Correct.
if we had, let's just say chocolate buttons, like
Yes.
sweets, you pick out a sweet, you got it, and then you looked at it and you're like, okay, this is a sweet, and then you ate it. So now you've got
Great.
a number of sweets.
Great. So let me just let's say we have a bag, right? And in this bag, we have some, let's keep with some easy for me to make is some blue marbles, right?
Yeah.
The three of them, right? And let's say some red marbles, right? Let's say four of them. So let's say we have a bag with some blue and red marbles. They are exactly similar except for the color. So that is what we're trying to say, right? Exactly similar except for the color. Now, what is the probability of taking up a red marble? It is because there are 4 out of 7, it is 4 out of 7, correct?
Yeah.
Now, let's say that we took one marble away in the first trial, correct?
Yeah.
Now, in the second trial, what is the probability of getting the red marble without replacement? This is called without replacement.
Without replacement. That would mean if one of the marbles decrease, the probability of getting a red marble would be a half or 3/6.
Correct. So in a way, the probability changes because the whole, the condition change.
Yeah.
Correct. Now,
Yeah.
this was a very short way of saying it, but actually, the answer will be slightly different. But this is only to tell you that if we are doing a conditional probability here, that is, if in the first case was red, right? In
Yeah.
that case, what was the probability of getting red again? You get the whole idea? Hmm?
Yeah.
And in that case, it reduces to 3 out of, and because one has been removed, 6. You get the whole idea.
Yeah.
Now let's look into the same question using our tree diagram. Okay. And
Mhm.
now we are going to find the right answer. Is that okay? That answer was not quite right. Okay.
Oh, okay.
So let's look into this once again. Okay. So what are we doing? So we have one bag in which we have 3 red and 4 blue marbles, correct? So now let's go to the probability of getting red or blue is what? Tell me, first time when you do it.
Well, the total is 7 for
So
getting
3 out of
red.
7.
Yeah, 3/7 for red
This
and 4
is 4 out of 7.
yeah.
So you see there are different probabilities in different branches this time, correct?
Yeah.
Now let's repeat this experiment. And now it is without replacement.
Yeah.
Now it is interesting. If I have already picked up red, so now we know total we have 6 left, correct? Because in the first case, we have already picked up something. It could be red or blue. We don't know, right?
Hmm.
We don't know. But if it was red, then the number of red has decreased to 2, and therefore it will be 2 out of 6, correct? To get
Yeah.
red next time. To get blue, blue are still 4 out of 6. You get the whole idea, right?
Yeah. Yeah.
That is what I'm trying to say. And now we are leading to the right answer, right? So now again, if I do red and blue, and let's say in the first case it was blue and without replacement, we don't know. In that case, now the blue is 3 and red is 3, right?
Yeah.
Therefore, probability for red is 3 out of 6, and for blue is also 3 out of 6, right? Both are 3 now.
So would we multiply both of those probabilities?
Yeah, now we will see how it turns out. So, of getting 2 reds, now the probability is you have to multiply 3 by 7 by 2 by 6, right? I'm not simplifying the terms, okay? I'm
Yeah.
just keeping them as such for, understanding it better, right? I don't want to simplify this to 1/3, okay?
Yeah.
Similarly, for getting red and then blue is 3 by 7 and 4 by 6, correct? For
Yeah.
getting blue and then red is 4 by 7 and 3 by 6. And for getting 2 blues, 4 by 7, 3 by 6, correct?
Mhm.
This is 2 blues. I should have written first. Make sense?
Yeah.
So you see how handy the tree diagram is to work with, right? It is a
Definitely.
complicated question, okay? We are doing conditional probability. without replacement. Correct. And now the question really was, what is the probability of getting two reds, right? I'm writing red, red, right?
Mm-hmm.
Without replacement. As you can see, it is 3 by 7 times 2 by 6. You get the whole idea.
Yeah.
Now, it is not 3 by 7 times 3 by 7. You get the idea.
Yeah.
If you would have replaced it, then it becomes an independent event where the probability of taking out red remains as 3 by 7. It changed.
Yeah, that makes sense.
So this is the conditional probability. This is the probability where the event is not an independent event, right? So not independent. So it is dependent event.
Would we call it not independent or dependent, or are they
Dependent.
dependent?
You can say it is not independent for sure. And dependent, yes, the other way. So we have understood how it is dependent. It is dependent on what really happened in past, correct?
That makes sense.
Right? All the probabilities would have changed. You could see of getting two blues or at least one red or no red. Any probability you can work out
Mm-hmm.
has been affected if the process involved is without replacement. If you do replacement, the things will change. It will remain as 3 by 7 times 3 by 7. You get the whole idea. Then it is independent event. You get the whole idea.
Yeah.
Because the environment did not change. Environment remained as 3 red and 4 blues.
Ah, okay.
That is
So
kind of important.
could we say that probabilities done without replacement aren't fair?
Yeah, no, no. We are not talking about fair and unfair. It is still fair. But the
Okay.
case is, if you do not do the replacements, things change and you get a different probability.
Ah, okay, that
Yeah,
makes
this
sense.
is also correct, right?
Yeah, yeah.
Normally, what we take from the environment, we don't give it back. So it is all fair, right? For
Yeah.
us, everything is fair, right? If we were giving back, then we could say, well, we are doing something which is fair. The other guy is not doing it. But now we cannot blame it because we are ourselves not giving it back, right?
Yeah.
So it's fair. That's another way of defining the terms, right?
Yeah.
Great. Now, last topic which I'm going to cover is very important, and it's called conditional probability. Have you done conditional probability?
I've heard of it, but I don't think I've ever done it.
Okay, so it's very good. You heard about it. So I will not use any formula to give you how do we find conditional probability. That's the beauty. The formula is slightly more complicated. Everybody gets confused about it, including myself. And therefore, since you are just in grade 9, right? I'll make you understand conditional probability. Well, let's take two dice, okay?
Okay.
So dice experiments we can do in many different ways, right? So I prefer, especially when we take two dice, making a matrix. So we have learned tree diagrams, right? And now we will see how to make a matrix to solve our problems, right? So if you throw a dice, let's say we could get these numbers 1, 2, 3, 4, 5, or 6, correct?
Yeah.
So this is, let's say, our dice 1 in this side and dice 2. I'll write here as numbers as 1, 2, 3, 4, 5, 6. Great. So now what am I looking at is when we add these two numbers, right? So what is the sum? We are looking for sum, right?
Mhm.
Two dice. And we want to find the probability that the sum is greater than, let's say, 10.
Greater than 10.
Okay. So how could we do this question? The best way to do is to make a matrix as I'm making one and fill
Mhm.
it up with the sum, right? So I'm writing plus here. So if you add one and one, you get two. And if you add one to it, so you get three, four, five, six, seven, right? It's easy to make. One plus two is three, and then just add the numbers. Do you see that?
Yeah, yeah.
One plus three is four. Keep on adding, right? And then five, six, seven, eight, nine, 10. And then 6, 7, 8, 9, 10, 11. And then 7, 8, 9. Maximum is 12, right?
Yeah.
Now, we'll look into this question as what is the probability of getting greater than 10? Can you tell me now from this table?
Greater than 10.
Yeah.
3 out of the whole.
Greater than or let's say equal to also.
Yeah.
Let's make it greater than equal to for now, so that we get more numbers, right?
Yeah.
Okay. So total number is how many? 6 times 6 is the total, which is 36. Do you understand?
Yeah, yeah.
So 36 is the total. I mean, and 1, 2, 3, 4, 5, 6. Is that okay?
Yeah,
1
that's
out
fine.
of 6. So sum being greater than or equal to 10 is 1 out of 6. Is that clear to you?
It's when conditional. Yeah, that is clear.
Now, conditional, I'll show you now.
Okay.
Now, conditional is so great. Let's say conditional probability. Let's say if I know that dice one, let's say we throw one by one, right? And
Yeah.
we throw the dice one, and we know dice one is 6. So the conditional probability now we are going to do, can I make it like this? Okay. So let's talk about conditional probability. Since the time is running out, I'll kind of rush through it, okay?
Yeah, yeah, yeah.
So conditional probability dice one, we get 6. Is that okay?
Yeah.
Now we want sum greater than equal to 10. What is the probability of getting sum greater than equal to 10 now when we know that the first die is 6? How will you do this? Difficult, right?
The first die is 6. Does
Yeah.
that mean it goes from 1 to 6 or just 6?
So first die I throw is 6. I'm very happy. I want a number greater than equal to 10.
Okay.
What is
Yeah.
the probability that when I throw the second dice, I get a number, sum of first and second as greater than equal to 10?
So basically, the question is asking what's the probability of getting a 4 on dice 2?
4 or more.
4 or more, yeah.
You are right. You have sounded so beautifully. Can you give me the answer?
Uh, since a fair dice only goes from 1 to 6, 4, 5, 6, that means there's 1/2, 1 over 2.
So, Supranshi, you're so close and so right.
Okay.
It is a case of conditional probability since we know the condition that first dice gave us 6. So how I do it is we know the first dice is 6. So we are looking in this column. Do you see that?
Yeah.
And in this column, we got only 6 numbers, out of which we 3 are favorable, and therefore the solution is 3 out of 6. And exactly what you said, the probability is half, not 1/6. Do you see the difference?
Yeah.
Probability is half, right? Because as Priyanshi just now said, it boils down to getting 4 or more in the second dice, where there are 6 chances. This is conditional probability. Do you see how easy it
It
is?
is definitely.
And
Yeah.
if you see the formula, which will be taught to you soon, you will think like, oh my God, how do I use it? Every student who's watching our video will be thinking about it, because they all use the formula and they get the wrong answer.
Okay.
Now, here is the second question, right? I'm not changing my question, Pranchi. We understand it carefully, right? So, conditional probability. I'm saying I have thrown the 2 dice and I have taken the sum. I know one of them is six. For one of them is six. I'm not saying
Yeah.
first or second. If I say one of them is six, what is the probability of their sum to be 10 or more? Can you tell me this answer?
If one of them is six, but we
One of
don't
them.
know which of them is.
We don't know which one of them. Correct.
Could we use a matrix for that? Like
Yeah, we
table.
are using the same matrix, which is on the screen.
uh, so I would just line it up so both of the dice are
Yeah.
on six, and then find the common terms, which are more than 10. Is that?
Okay. So tell me the answer. Let's line up. You mean this line up?
Yeah.
And now tell me the answer.
I mean, I can only see them colliding at 12. Oh, I'm not really sure. I get it, but I don't get it. Can
Okay.
I?
So one of them is six. We don't know which one, first or second, right? We know one of them is six, and we need a probability of 10 or more. Should it be higher than half or less than half? Can you tell me this?
It'll be lower than half.
Okay, so let's figure it out, right? So you were halfway correct. That is to say, it's a tricky subject, Priyanshi. No one understands, including myself. Okay, so don't worry about it. We're just trying to figure it out, right? On the screen this time. Okay, so we have how many total sample, right? Let's count total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Do you see that?
Yeah, yeah,
Out of 11, 10 or more is how many? 3 to 5. Do you see that? So the
yeah.
answer is 5 out of
Oh,
11.
I was close. I was close.
You're very close because your answer is also right. It is less than half.
Yeah,
Do you see how easy it is? We have now solved a conditional probability, very difficult question where we have thrown two dice. One of them is 6. We want to know the probability of 10 or more as the sum. And it comes out to be 5 out of 11 simply from our matrix. You see the power of matrix?
definitely. Yeah,
Perfect. So, with that, we are going to end our class today. And Pranchi, you can summarize what we have learned today, right?
yeah.
Yes.
Um, I think I did a summary halfway through. So should I start from there?
After that, yes.
After that, we looked at independent and dependent events. Independents occur with replacement, so there's no interruption in the
Correct.
process of that event. But when we have a non-dependent or dependent event,
Correct.
um, it there's often uh, it's done without replacement, so something happens to the experiment, so that like the overall events possibilities lessen. Then we looked at conditional probability,
Yeah.
where we looked at the sum of two dices being less than or equal to 10.
Correct.
We could display this with the power of the matrix,
Correct.
a, which is a great way of representing the total outcomes we can get. Using this, we could figure out lots of probabilities on the
Yes.
basis of different conditions. So
Correct. Great. And next class, we are going to explore Venn diagrams and how beautifully Venn diagrams can be utilized in probabilities and beyond, right?
yeah,
So that's where we are going to end the class today. It was wonderful working with you, Pranshi, and
thank you.
you're so bright. You gave some very brilliant answers. I'm extremely happy about it. You're learning fast. Okay, then. See you next time. Bye for
Thank
now.
you. Bye.
Thank you.
Who is this book for? Middle and high school students who want to go beyond the classroom? Future STEM leaders looking to develop problem-solving and analytical skills? Anyone who loves math and wants to see its real-world applications in AI, physics, and engineering.
Are you ready to explore the mathematics of the future?
Crack the numbers for future STEM leaders. Sharpen your skills, shape the future. Available soon. Visit our website to pre-order your copy and unlock your mathematical potential today.